So this is a so I gave a version of this talk during the Open Research Forum like that happened like a few weeks ago. And this is a re-recording of this same talk. So today I'm going to talk about symmetries, which I find as a very fundamental and important topic that pervades all of mathematics and physics. And I think introducing this topic to you can be helpful, like whatever topic you're going to pursue after this. So I hope this talk will be useful and hopefully also accessible to everyone who's listening. So let me just start with an easy exercise. So I've tried to draw some triangles, and I would like you to identify out of these 5 triangles one of the figures that you find somehow the most symmetric. So this is maybe I'll give you like a few seconds. You can think about it. Out of these 5 triangles, which one do you find as the most symmetric figure? And maybe someone can just speak up and try to share their ideas of which one do you think is the most symmetric triangle and why would you think so? So anyone?
Just like the second one, the one that's like isosceles.
Second one?
Yeah.
So this one, right?
Yeah.
So, right. So I agree that most of you will also agree that this isosceles triangle is somehow more symmetric than, say, some scalene triangle, such as this one. Okay, and why would you argue so? What's something special about this isosceles triangle?
Like so in an isosceles triangle, like, the 2 sides are like equal. Like 2 sides are like equal in the terms of length. So
right. So the observation is that somehow these 2 sides are equal, and that's some sort of property that's not present in triangles such as this one or this one. But we also note that so although my attempts to draw these triangles were pretty miserable, that you might have not noticed, but for example, this one is also supposed to be like a right isosceles triangle, and this one sort of has the same symmetry such that these 2 side lengths are equal. And in fact, the one I was aiming for was this final example, which is supposed to be an equilateral triangle, such that all these 3 sides are the same. So somehow this regularity that all of these angles and the sides are the same in these particularly symmetric examples, the examples that fit your intuition of symmetry more. So the common characteristic is that you find this some sort of regularity in these particular examples. And mathematically, what the fundamental observation is that the really crucial fact about these regular objects, the objects that we find the more symmetric, is that somehow they admit more transformations that leave them invariant. So that's the key observation here, is that regularity means that you have some sort of extra structure to your object. And this extra structure allows you to have more transformations that leave that structure invariant. And in the case of equilateral triangle, or if we go back to these examples, the fact that you have this regularity such that these 2 sides are equal, which is the aspect of the symmetric object that you have identified, the key fact is that this triangle admits more transformations that leave this triangle invariant. Namely, you have this reflection along this altitude such that if you reflect this triangle across this axis, you would still get the same triangle. But you don't have this transformation for examples such as this one or this one because you don't have this regularity. You don't have these two sides that are equal, and therefore you don't have this reflectional symmetry. And the fact about equilateral triangle that would make it more symmetric than these isosceles examples is that because the three sides are all equal, you have even more transformations that leave this triangle invariant, which I've drawn here as three different reflectional symmetries of the same object. And in fact, it turns out that you also have these rotational symmetries for this equilateral triangle, rotation along 120, 240, 360 degrees. And these, in fact, and these indeed, for equilateral triangle, give you these examples of more transformations that leave this triangle invariant. And that's a key point. So the mathematical study of symmetries is really not about this intuitive or sort of naive idea of regularity, but really the key point is that when you have such regular and symmetric objects, you have more of these transformations. And the definition, the mathematical definition of symmetry is that transformation that leaves some sort of geometric object invariant under some structure that you're giving it. Okay, so that's really the main point that I want you guys to remember from this talk is that symmetry is really these transformations. Okay, so why should we care about symmetries? So that's sort of the next natural question that you might want to ask. And I'll try to give you some sort of vague reasons or sort of heuristics of why you might care about symmetries. So first is that symmetries are sort of beautiful. So symmetric objects have been motives of all different aesthetic attempts throughout our history. So these are some arts that coming from ancient civilizations. You can already see that the idea of symmetry is already incorporated into their work. So indeed, I think this one is from Sumer or something, and you have this reflectional symmetry coming up in the art. And for these examples, you have these translational symmetry, such that you shift this art by this, 1 unit, and you still get the same type of art. So these are still the same examples as the triangle examples that we were considering. And somehow, us as humans really somehow naturally find such symmetric objects as beautiful, and that's already an interesting and that's already like a reason that we will find these symmetric objects, and therefore the study of symmetries as an interesting topic to pursue in mathematics or even in aesthetic philosophy. So that's sort of one reason you might why you might care. Another reason, maybe more I don't know, plausible for preferable for people who care more about science, is that symmetries really occur very naturally in all sorts of different mathematical and physical contexts. So there are some examples that I've brought to you. You can see that a lot of life forms already have this symmetry in their development. So butterflies, for example, have this reflectional symmetry. Humans also have this reflectional symmetry. You can also see all sorts of different symmetries really naturally occurring in different contexts in biology. And you can also see examples in chemistry and physics. For example, if you look at really microscopic scales, you would microscopic scales. If you look at, say, examples such as crystals in chemistry, they also enjoy this extra sort of rigidity and regular structure, and therefore some sort of complicated symmetry transformations and the study of these symmetries are really natural in the study of the chemistry of such objects. So in this case, if you look at the interaction between these microscopic atoms, you have this complicated translational and rotational symmetries that really leave this crystal structure or some sort of interaction structure between these atoms invariant. So such symmetries also occur in chemistry as well. The last example I'm showing you here is something called fractal. And here, this structure is something that is self-similar in the sense that the symmetry transformations that leaves this structure invariant is that of rescaling. So if you look at the same picture and if you increase the resolution and sort of try to zoom into a particular part of this picture, you would still see the same picture. So that's also some sort of transformation. So you're changing your resolution or changing your scale, and these objects are left invariant by such symmetries. And these fractals, you might have seen in different contexts. They come up a lot in biology. They also come up as really inherent structures if you study statistical mechanics or even quantum mechanics. Really, the understanding of these fractals are really crucial to understanding such subjects. So therefore, symmetries really come up in all different contexts if you're studying science, and therefore, these are important topics to know about. So I'm just still trying to persuade you why you might care and why you should bother to listen to today's talk. Maybe the last reason I might give is something more mathematical, is that symmetries are really useful in mathematical contexts, because whenever you have some sort of symmetric objects, when you're studying math, you encounter some of these symmetric objects. That means really these objects have extra regularity and therefore more structure to them, and hence more transformations that leaves the structure invariant. And in fact, by exploiting that sort of regularity in your objects, that really allows you to say more about such objects. So for example, in this equilateral triangle example, in your geometry classes, you might have learned different facts about triangles, but you learn more facts about equilateral triangles. So for example, you learn that the ratio of the edge and the height should be 2 to the square root of 3, or you learn the fact that the circumcenter, incenter, centroids are all the same, so on and so forth. You can say more about these equilateral triangles compared to generic triangles, precisely because these regular triangles or equilateral triangles have these extra symmetry to them. And therefore, knowing about this symmetry allows you to exploit such knowledge and therefore say more about some particular objects that you care about. Another important problem in math is that of classification. So say if you want to classify all different regular polygons, you know that there's exactly one convex polygon of, say, n edges, such that the edge length of all of the n edges and the angles, all the n angles have to be the same. So you can really classify those regular polygons. If you're trying to classify regular polyhedra, that's a harder problem, and that has a more interesting answer because although in the two-dimensional case, you have this infinite family of regular polygons, in the three-dimensional case, you know that there's only 5 of these convex regular polyhedra. And the reason you can say something so fantastic like that, some sort of complete classification result, you know that there are only 5 different regular polyhedra, is because you're exploiting this particular rotational symmetry of these objects. And you can say something about these rotational symmetries. You can really classify these things, which is in general very hard. It's very hard to classify, say, all different polyhedra, but the same problem if you're try to classify regular polyhedra, now that's a problem that can be answered and has an interesting answer. precisely because you're asking this question with this extra regularity implemented to them. Okay, so so these are sort of my 3 reasons of why we might care about symmetries. And from now on, I'll try to sort of illustrate this topic in a more hands-on sense by giving you a lot of examples that you might care about or you might have already seen in whatever mathematics classes that you've been taking so far. Okay, so any questions at this point? All right, so I'll try to just show you a lot of examples and work through these examples with you so that you can get a more hands-on experience with this concept of symmetry and transformations that leave this object invariant. So for example, this regular triangle, we have already identified all the symmetry transformations. In this case, we know that there are these reflectional symmetries, and we also have these rotational symmetries given by rotations by 120 degrees, 240 degrees, or 360 degrees. So these completely classify all the possible symmetry transformations that you can consider on this regular triangle if you want to leave this form of triangle exactly invariant. Okay? So maybe we can try to work through this example together. So this is a regular four-gon. In other words, it's just a regular square. And can somebody help me identify what are the possible symmetry transformations that you can consider on this object?
Rotation.
Rotations, okay. Rotations by how many degrees?
90, 180, 170.
Right, great. Exactly. So these give you some. This is really easy example, but this already gives you an insight, such that you know that because this square is a regular four-gon, you know that rotation by 9 degrees is one of these transformations, symmetry transformations. And as soon as you have such transformation, you know that you can also compose or repeat these transformations over and over, and you would generate more such symmetry transformations. And that's exactly what Kensuk did, right? Because you as soon as you have this 9 degrees rotation as one of your symmetry transformations, you also have 180, 270, and 360 degrees as well. 360 degrees, you repeat this rotation once more. That's the same thing as this thing. So you're going back to your example. Okay, and are there any other symmetries that you can consider on this object? Anyone else?
A reflection.
Reflections, yeah. So exactly just like the triangle case, we also have this extra reflection, say along this axis and this axis. Are these all so reflection along these two vertical and horizontal axes are also symmetries of this object. Are there anything else? So can anyone identify more symmetries, or is that all?
Diagonal.
Right, exactly. So diagonal reflection along these diagonals are also symmetries of this object, and you can in fact use my previous remark that you can repeat or compose two different transformations to get a new transformation, and you would easily identify. You can sort of easily check that if you try to compose 9 degrees rotations with one of these vertical or horizontal reflections. So you do the rotation and then you do this reflection once, then the resulting transformation is exactly going to be one of these reflections along the diagonals. And in fact, just like the triangle had these 6 different symmetry transformations, this regular foregon enjoys 8 different symmetries. Okay. And you can really generalize the same idea to general regular n-gons. You know that there would be n reflectional symmetries and rotational symmetries if you're considering a regular n-gon. So that gives you 2 n different transformations. And if you look at other symmetric objects, such as these regular polyhedra, here I've drawn you a regular tetrahedron. You have these sort of complicated rotations that leaves the tetrahedron invariant. You can also consider certain reflections along some planes in 3-dimensional space, and you can work this out yourself. You would see that there are 24 different transformations that leave such tetrahedron invariant. Okay. So as I've said before, the fact that you have these 5 different regular polyhedra is exactly really about identifying what kind of different rotational symmetries you can have. And it's actually not a too difficult exercise to find out that these are the only 5 possible cases that you can have. If you're considering rotational symmetries in 2 dimensions, you have these sort of finite subcollections of rotations that leave some regular n-gons invariants. In 3-dimensional rotations, if you're trying to find such sort of a finite subcollection of possible rotations, you would see that the possible symmetries really restrict you to have these 5 regular polyhedra as the only examples in 3 dimensions with finite rotational symmetries. And that's really something really remarkable and fantastic, but it's really not emphasized very well in our, say, middle school curriculum. The fact that we have this infinite family of regular n-gons for 2 dimensions. If you try to ask the analog of the same question in 3 dimensions, you have this drastically different answer, that you have only these 5 examples. And that was something really remarkable to ancient Greeks, and it's still a very clean and complete classification result. But somehow I don't think we're emphasizing this too well when you first learn about this. That's sort of just my side remark. So I've given you a lot of geometric examples, and now I'll try to motivate the idea that the idea of symmetry can be generalized into more contexts that that don't really restrict you to this specific geometric objects that we're considering in 2-dimensional or 3-dimensional case. But my first example would be this, again, something geometric. So this is a two-gon, something. A two-gon like this, you can't really realize this with straight edges in 2 dimensions, but this is some object with 2 vertices and 2 edges. And you can see that there are 2 possible transformations that leave this thing invariant, which is either leaving it alone or making a 180 degrees rotation. You would just still get the same two-gon, right? And you can also see in the same example that you have this reflectional symmetry as well. That's also some other symmetry you can consider on this object. In this context, let's try to just focus only on the rotational symmetry, because I want to illustrate some points through my following examples. So here's my first algebraic examples. So have you guys all learned about complex numbers in your algebra class? So the complex numbers are just linear combinations of two real numbers. Linear combinations of one and this some number, the square root of -1, called I, with real coefficients. So you're considering these pairs of real numbers, and these are really fundamental objects that you learn in high school algebra. And if you consider this as a two-dimensional real plane, then you soon notice that you have this reflectional symmetry along the real axis. So that gives you an symmetry transformations acting on the set of complex numbers. So you have this transformation called the complex conjugation. So this is a transformation that sends complex numbers to the complex numbers, just like rotation sends a triangle to a triangle. And it leaves the set as it is. It sends a plus bi to a minus bi. And that's some sort of transformation, symmetry transformation you can consider on this algebraic set. So although that might look slightly different from our previous geometric examples, that's really not any different, okay? And we always have, this is one other point I want to emphasize, is that for any set and for any structure that we're considering on such set, we always have one trivial transformation, which is doing nothing. So that's the identity mapping that sends a plus bi to a plus bi itself, is leaving everything invariant. That's again is a symmetry transformation, but that's something that's a transformation, but it's a stupid one. It's doing nothing, right? Just like 0 degrees rotation would do nothing on your say square or triangle. All right. So I'll give you more algebraic examples. Say you're looking at the set of even integers and odd integers, and the possible symmetries you can consider on this set is that, okay, maybe you can add an even number. So that would send the even integers to the even integers. And so that will send odd integers to the odd integers, because adding even numbers don't change your parity. So that's the analog of the stupid transformation or the identity that we were considering, because it's leaving this class of even and odd just like they are. But you can also add odd numbers. Now that would do something non-trivial to your set. So the even integers are now sent to the odd integers, and the odd integers would be get sent to the even integers. And if you learned about any sort of, say, number theory when you were doing competition mathematics, I think a lot of people in the math circle have some experience with some mathematical competition. If you learn about modular arithmetic, what I'm saying is that exactly like modular 2, so mod 2 addition gives you this symmetry on the set of, say, even and odd integers, which are correspond to numbers that are 0 or 1 mod 2. So that's another algebraic example, okay? And another example is you look at the set of two numbers, +1 and -1. And you're considering two different transformations. One of them is multiplying by 1, which is leaving both of your elements invariant. The other one is multiplying by -1, which switches your element. Okay, so that's another algebraic example considering signs on real numbers. Okay, now hopefully I've bored you by all of these 4 examples, because in fact, really what I've shown you, these are 4 different objects coming up in 4 different contexts. But if you're really considering the symmetry transformations on these objects, they are really the same in the following sense. If you're looking at the transformations allowed in these objects, you always have 2 of them. One of them is a stupid one, which does nothing to your object or leaves your object exactly as it is. And the other one is some sort of non-trivial transformation that does something that is non-trivial to your object, but still leaves your object invariant in the sense that the set as a whole stays the same. And in all of these four examples, you can look at all of these four examples. You have this one transformation that does nothing, and the other one that does something. And the common feature is that if you repeat the blue transformation twice, you would get back to the red one. And really, the point of all of this is the insight that if you're really caring about symmetries, then what you should really focus on is the transformations themselves. You don't really need to remember all whatever the underlying set is, what the exact transformation is doing on the object, and that's irrelevant if you're studying symmetries. If you're studying transformations themselves, what is really important is how the transformations themselves are related, not what the underlying object or how the exact transformations on the object is being done. So that's sort of a conceptual leap, because now we're moving on to the realm of abstract algebra, where now we're saying that, okay, we don't really care about these specific examples, but now we're working on this abstract framework where any object can go into this object X, and we were focusing on these transformations only. And the important thing is that there's one transformation that does nothing, and another transformation that if you repeat twice, then you get back the trivial one. Okay. So the mathematical study of the abstract algebra of such symmetries is called group theory. So a group is just a math jargon that we use to consider these set of transformations acting on some object. So if you have some object X in whatever mathematical context or setting you're working in, if you have some object X and if you have symmetry transformations, you collect all those transformations acting on your object, and the set of such transformations is called a group. And the four examples that we were considering before, they all show you the same group, although the underlying object were different. The groups are the same in the sense that you have these two transformations that are related in the same way. Okay. And another math jargon to express that idea is called that of isomorphism or isomorphic groups. So if you have two groups coming up in two different contexts, if you can rename all the elements, you just forget about the underlying set. If you can rename all the transformations so that the one corresponds exactly to the another, then you say the two groups are isomorphic. And indeed, what I have shown you is that in these four different contexts, we have these isomorphic groups. So really, they were the same example, although the underlying set and the exact transformations were different. And just as an aside, this symmetry, this group where we have these two elements, one of them doing nothing, and the other one that when repeated twice does nothing, it's called a Z-mod 2 symmetry, as an analogy to the modular 2 arithmetic that we were explaining when we were talking about parities. So that group is called the Z-mod 2 symmetry or Z-mod 2 group. Okay. So in the study of these symmetries, so mathematically that's called group theory, because it's a theory of groups, which are exactly these symmetry transformations. And the point of abstract algebra, why we might try to do something so abstract like that, why we might try to forget about underlying set and really work with this abstract concept of transformations only, is that somehow by understanding this general abstract theory, then we can apply the general knowledge we have about general symmetries to specific instances that we would encounter in our mathematical journey, and get insights in those specific instances that we're actually working in. So the idea is that you look at different examples, you look at different examples coming up in different contexts. You find the analogy between those objects. You find what's common between them, and using that observation, you build up this abstract theory. And when you understand something about this abstract theory, now you can work backwards, and that when you're studying something new and you encounter some sort of symmetry, then if you know something general about symmetries, you can apply the general knowledge of group theory in your context, so that it can be useful to your specific case. So that's the point of abstract algebra, is to make this general theory that can be applied in different specific cases. But when we're making that theory, we're really building that theory by looking at different examples and try to find what's common between them. Okay, so when I was giving this talk in the Open Research Forum, I concluded by introducing one specific example of one sort of historical example of how group theory has been helpful in the study of mathematics, by telling you the story of a search for a formula for roots in the quintic equation. But maybe for today's schedule, maybe that's a good point to stop. So if you have any questions, I'll be happy to.